me give you an introduction to our syllabus. Okay, so this is the syllabus that we are going through for the coming days, and within this 5 days I will almost completely cover this syllabus, and I will also provide you the slides and everything at the end of all the 5 days session. Okay, so the first thing is about the space mission, type of space mission, flyby, impactor, etc. That is almost about the space missions and its importance. And the second session is about telescopes, types of telescopes, and major observatories and neutron observatories. So we can hardly say that, or we can overall we can say that it is about space mission and it's about telescope. That are the two major topics that we'll be covering in this session or in this whole 5-day series. So since space missions and history of space exploration, important manned and unmanned mission, all these things are connected, I will go to that only after the first 2 days. That is today and tomorrow I'll be discussing on telescopes mostly, and the next day, after the third day onward, I will be dealing with the remaining portions like the space missions and satellites, etc. Okay, so today and tomorrow is entirely dedicated for telescope and related stuffs. Okay, so with that intro, let me start my session. Okay, once again, welcome you all. So we will start about telescopes, and the session will go like why we need the telescope and what is basically a telescope and what is not a telescope is, and what are the different types of telescope that we usually have. That is something that we use for the daily observational purpose, something like an amateurs do, or maybe you are interested in buying a telescope, or if you need a telescope, that kind of telescope will be discussed in a brief. And most importantly, we will discuss about the professional telescope that are there in the Earth, and even in space there are telescopes, as you know. Okay, so that will be discussed in the in this session. So what you are seeing here is, usually we may think that this is not a telescope because this looks like a dish antenna. So this kind of antenna we use for gathering TV signals or something, like sometimes for radio signals, kind of that. And we may first look, we want connected with astronomy or space, or it is not connected to, we may think that it is not a telescope at all, but again, this is a telescope. So what kind of telescope it is, you might be already knowing, but anyway, we will discuss about it. So before going to that, let's discuss what is a telescope is, or why we need a telescope. And I will give you another intro before that, something about the light. Okay, so in astronomy, when you hear the word light, okay, so in normal case, when you hear light, so already you know that, so light is coming from your screen, and that is why you are watching this session actually. And I can see your faces in my screen. That is because there is light is coming. So that is only one type of light, which is our eyes, or we have our own eye, that I can see a specific type of light. Okay, so the light that humans can sense, okay, human being can sense, that is sometimes called visible light. Okay, that is always called as visible light. So why it is called visible light specifically? Because there are some other kind of, there are many types of light, or they are called invisible lights. Okay, so it is invisible to human beings. So there are invisible lights are there in the universe, or even in our nature it is there, even around you it is there. Okay, suppose in your mobile phone you might be using a Wi-Fi signal to receive the internet. Okay, so but you are not seeing anything that is coming from your Wi-Fi antenna to your phone. Are you seeing anything that is any signal that is some light ray or anything? You cannot see anything. Okay, or while receiving a mobile phone call, you won't see anything. Like if you have any experience with the X-rays, so if you go to take an X-ray with for your bone and all, then you won't see any flash coming there. And in a microwaving oven, the cooking is happening not with something like a fire or anything. There is also another kind of wave that is being used, which we cannot see. And here you are seeing this picture. This is actually a photo of that is taken in another kind of invisible light called the infrared. Okay. Okay. Yeah, okay. So in infrared, so infrared is there. So when you are listening to radio, you can see something like a radio antenna will be there, but you won't see any direct light. So in all these 4 pictures, you can see here, 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 here it is being used a specific signal called or light called X-ray. And in microwave oven, as the name suggests, it uses signal called a microwave signal or microwave light. Okay, so I'm specifically calling it as light. Okay, and this photograph is actually an infrared, infrared light. Okay, it's taken. And when you receive a Wi-Fi signal or maybe some radio, when you are listening, they are all working on a type of light called a radio. Okay, why I am mentioning all this invisible light? Because in our nature there are many other kinds of light. Like here you can see a list of them, starting from gamma rays, X-rays, ultraviolet, and a tiny part of visible light that is only that we can see with our own eye. Then there is infrared, microwave, radio wave. So apart from this visible light, all the six others which we cannot see, but we have instruments. The scientific community has already made instrument which is able to sense these lights. So why I am mentioning here, what is the importance of that in astronomy? Because if you observe the night sky, okay, we can see stars, maybe some if you use a telescope, you can see the planets with a ring, maybe the Jupiter moons, or maybe some galaxies or nebula, etc. But if you were able to see, that are only in the visible light. But there are other lights are also coming from the universe. Something like infrared is coming from the universe, the X-ray is coming from the universe, gamma ray is coming from the universe, radio waves are every wavelength or every kind of lights are actually coming from the universe. So in astronomy, when we say generally light, okay, all these things are actually light for astronomy: visible light, ultraviolet, X-ray, gamma ray. And scientists have made, astronomers are actually made and using telescopes that works in all this wavelengths. So the usual telescope that we bought from the market and use for simple stargazing, that works only in visible light. And the first title figure that you are seeing here, this is not a dish antenna. This is basically a dish antenna, but this is a telescope which is working in radio waves. Okay. Anyway, we will discuss about other telescope as well, and I will show you some examples here. Okay. But I'm not going to the details of it here, but we will go to individual details of the major telescope that is shown here. So here you can see this is an X-ray telescope. Okay, so this telescope works in X-ray. It does have a mirror. Its technology is a bit different. Okay, but anyway, this is called an X-ray telescope, and this is basically the Chandra X-ray telescope. And hopefully, this second figure you might be knowing, the famous JWST, the James Webb Space Telescope. As you know, it works in infrared. Okay, this is not a visible, and this is the most famous space telescope, maybe telescope I will say, that is the Hubble Space Telescope, which is shortly known as HST, and this works in visible, that is the normal light that we can see, then in ultraviolet and some infrared as well. So it has the capability to see in 3 different types of light. And what you are seeing here, this dish antenna, as already mentioned, this is a radio telescope. Okay, and what you are seeing here, this is a normal visible light telescope. Sometimes it can see some infrared as well, but anyway, usually we can call it as visible light. Okay, so these are all different types of telescope based on, or we can classify the telescope based on what kind of light it is being observed. Okay, the kind of light means what is here, whether it is observing on gamma ray, X-ray, ultraviolet, visible light, infrared, microwave, radio wave, etc. So based on this, we can actually classify the telescopes into that kind of. Okay, so we can call it as radio telescope. We will get to some major or most famous telescopes in this category for sure. Anyway, this is one example that I have given an overview of types of telescope that usually there are. But anyway, before going to that, let's discuss about what is basically a telescope, or why astronomers need a telescope. Because we have a beautiful eye already, and why we need a telescope. Okay, so just a second. Okay. Okay, so why we need a telescope? So one example is that, or one idea is that we need telescope because then only with our own eye we can only see the visible light. To see in other light, something like the X-ray or maybe radio or infrared, we need telescopes. Just leave that for a moment and let's think basically, even though we can see invisible light, why we again need a visible light telescope? So the idea goes like this. So this is basically our simple eye, you can see. And if you go to a open space at night without a moon on a new, imagine that it is a new moon day and there is no moon at all. So you are in a very dark location and you are trying to stargaze actually. And if you stay there for a while, you will start to see more stars. And if you start to count the number of stars that are there, and you will only see, you won't see something like the billion or millions of stars, you will only see some thousand of stars, something like maybe 2000 or 3000. That is the maximum number of stars that we can see with our bare eyes. Okay. Why? What is the reason why we can only see that much number of stars? As you know, there are billions of stars even in the Milky Way itself. Why we can't see that those billion of stars? At least some lakhs of, or maybe some at least thousands or 10,000s of them. Why can't we see? So that is why, because our eye has a problem, or the eye is evolved not to become an astronomer. I evolved to become a human being to walk on the earth or to live on the surface of earth. So anyway, our eye has something called this black opening, and this opening is known as pupil. As you know, this opening is called a pupil, and the size of the pupil is not constant. It keep on changing. So why it is changing? Because when you are in a dark situation, something like when you are stargazing, the eye's pupil should be something of this size. It should be bigger. Why it becomes bigger? Because, or we formally call it as, it dilates. Why it dilates? Because you need more light at that time. When you are in a dark situation, you need more light. So to accommodate or to get more light into the eye's pupil become larger. So the opening is bigger, means more light can enter. So more light can enter means you can see more stars, or maybe in other case you can even see something in a dark situation. That is why our pupil become dilated, or simply we can call it as it becomes bigger. But what is the maximum size our pupil can become? So it is something like maybe some 5 to 7 millimeters only. It is even less than a centimeter. So it is so tiny, we cannot make it even bigger. So that is a problem with our eye, or that is a limitation of our eye. If our eye can be opened, this pupil can be opened, something like our mouth, as big as our mouth, we could have been seen the Milky Way so easily, even from a uh, uh, less polluted sky, or we can see very easily, we can identify the Andromeda galaxy in the sky, or we can easily identify the Orion Nebula in the sky, or we could have been seen a number of stars, maybe 10,000 or 50,000 of stars can be seen if we can open our pupil something like as big as our mouth. But the problem is that anyway, we cannot open it like that. It is limited. Okay. So now, is there a way to open it without doing any surgical procedure? That is where the telescope comes. So just imagine that you have a bottle here, and in this bottle, I want to collect some water. Okay. So something like in a rain. So the rain is pouring from all the direction, something like this. Okay. So that I can actually fill this with the water. Okay. So that is my plan. But the problem is that here the opening is so small, so that what I can do, it will take a long time to fill this bottle. But I can connect another interesting instrument called a funnel, so that this funnel can collect the water that is falling all over here, so that the bottle will fill faster. In a similar way, I can place a kind of a funnel, but not this funnel. This funnel won't work for my eye because it is only for water or some liquid and all. This won't work for my eye. Anyway, it cannot collect light, so that it won't work basically. But the concept is same, so that I can take a lens. This is called a lens. What kind of lens? This is called a convex lens. And the convex lens has the ability to collect light from one side and to get focused into a single point. Okay, so it works like a funnel. Okay, funnel for light. So we can simply call it as a light funnel. Okay, now using this light funnel, I can actually concentrate light, and using it, I can make a telescope. Okay, just leave this equation. Okay, just leave this. And I can make a telescope called a refracting telescope. Okay, so this has a primary lens. So just with a single lens, you cannot make a telescope. We need an additional lens through which we are actually looking. So our eye will come somewhere over here. Okay, so these are the eyebrows. Okay, it may looks like something else. I don't know. Anyway, this is an eye. Okay, so through this eye, I can observe, and this lens is called an eyepiece. So this eyepiece, and there is something called objective. This objective will be pointed towards the object that we are looking. For example, if you have a planet like Saturn, if I am observing the Saturn, this objective lens will be towards the that particular lens. Just a second. Okay, so that is about the refracting telescope. So why it is called a refracting telescope? Uh, you might have been learned in school class, that is, light has a special interesting property. Usually we say that light travels in straight line always, but there is an interesting experiment, something like if you take a glass of water, okay, not full of water, half of water. So this is here, this is water. Imagine that here it is half filled glass, and if I shine a laser light and fill here with some smoke or something to identify the path of the laser, then that laser beam will go like this into this water, and when it reaches the surface of water and when it enters to water, this path won't be the same. Okay, it will slightly bend. I am actually exaggerating here. It won't bend this much. Anyway, you can visibly see that bend. That is something like this. So this bending of light, when light is passing through two different medium or two different media, that is called refraction. Okay, that phenomenon of light is called a refraction. The lens is basically a glass, okay, but it is polished in a specific way or shaped in a specific way, so that when the light passes through this, the light get refracted. Okay, light get refracted and will focus and all. So the lens basically works on the principle of refraction. That is why it is called a refracting telescope. Okay, so the lens is working based on the refraction, and the telescope is made using basically using the objective as a lens. Then we call it as a refracting telescope. Okay. Okay, so then I think there is some discussion or doubts are going on in the chat. I think I will clarify that at the end for sure. Okay, so the problem is that if you spam with a lot of discussion, the problem is that I will get unnoticed the main questions basically. So, okay. Uh, and one more interesting equation is there, if you know, that is to find the magnification. Okay, so the first equation that we have seen in this previous slide that I am not discussing for you, this is for the senior student, but I included that in the slide. So whenever you are in your higher classes or something, you can come back and refer to this if needed. Okay, that is why I included, but don't worry. But I will introduce you to an equation here that is called the magnification of the telescope. So how much an object is magnified through a telescope that you are looking. That depends on the focal length of these two lenses. So let's see what is the focal length. So already we have seen, if you place a lens like this, when the parallel light beams comes from one direction, it will get focused. Okay, it will get focused to a point. So that focal point, or the where the light focuses, and the distance to the sun lens. Okay, so the distance between, roughly the distance between the lens and this focal point is called the focal length of the telescope, or we denote it by the letter F. So since here in this telescope we have two lenses, that is, one is the objective lens, the second is the eyepiece. So both has a focal length. So the focal length of the objective is called FO, and focal length of the eyepiece is called FE. We are just denoting it with the letter. So if you want to find the focal length or the magnification of your telescope, you can actually divide the objective lens focal length with the eyepiece. Okay, so that is the simple way that you can. I will give you an example. For example, assume that the objective focal length is 50 centimeter and your eyepiece has a focal length of 10 centimeter. So just simple divided 50 centimeter divided by 10 centimeter, which is equal to 5 times magnified. So that is how we can easily calculate the magnification of a telescope. Okay, refracting telescope. The same will apply for the reflecting telescopes. Okay. So there is one more interesting, two different designs are there. Usually when we use a telescope, sorry, okay. So usually when we use a telescope, the second lens is usually a convex lens. Okay. So the second lens will be a convex lens. So this is called the Kepler design. So anyway, the first lens, the objective lens should be always a convex lens, whether it is a Kepler telescope or a Galilean telescope. For the both, the primary or the objective lens should be convex. The second lens can be chosen either a convex or a concave. If you choose a concave design, so concave means the lens is actually curved inward. Okay, something like this. If you use a concave, then it is called a Galilean telescope design, and this is called a Kepler telescope. So why it is called a Galilean telescope? Because Galileo used this kind of a telescope to observe the night sky. So one advantage is that, and effectively the length of the telescope will be so small as you see. Okay, so that is about it. Okay, so this is about the. And now there are some issues with the this lens telescope. One is called the spherical aberration. Okay, so the spherical aberration is that something like you can see when you use a magnifying glass or something, you can see the center part will be sharply focused. Here even you can see, and to the edge there will be some blurriness. Okay, you can see this blurriness, and this is called a spherical aberration. So this spherical aberration is a problem of the lens, and also there is something called a chromatic aberration. Here you can see when you look through some lenses, you can see some colorations. Okay, so this is not the actual color of the object that you are observing, but this is it. So if you tried to make some basic telescope using just some couple of money or a couple of bucks, if you can buy some two convex lens, and you can actually simply make a telescope using some pipes and all. And if you make something like that, you will see some colors like this, and you will see this aberration as well, because this is inherent with the usual lenses. But there are ways to avoid this. But the better way to avoid all these issues and to make bigger and bigger telescopes. Now the question is, why need bigger and bigger telescope? Okay, so scientists are always trying to make bigger and bigger telescopes. Okay, bigger in the sense that what is the size of the telescope? That means it is something like, imagine our old funnel. Okay, so imagine our old funnel. So assume that I have a funnel like this and you have a funnel like this. Who gets more water in a short amount of period? Okay, you for sure, I know that this will collect more water in a short amount of time, and this will only collect a less amount in a short interval of time. So we need bigger telescopes to collect more light. Okay, so for making bigger and bigger telescope, the lenses are not actually convenient, and it is costly. It is not easy to build it mechanically. It is not that easy to balance the weight. There are several problems out there. Even in the mechanical design also there are issues. So there is another way of building a telescope that is using something else to focus the light, that is called a concave mirror, or we can call it as a converging mirror. So concave means it will be curved inwards. So usually the mirror that we look is usually a flat mirror. Okay, something like a flat mirror, but the reflecting surface can be curved inward. So this, if this is the reflecting surface, something like this, then it is called a concave mirror. Similarly, there is another one that is a convex mirror. So okay, so this is called a convex mirror, and which actually another kind, but we cannot use it for making a telescope. Anyway, concave mirror can be used because again we can use it to burn paper like a lens. What is the meaning of burning a paper using a concave mirror? The idea is that it can concentrate light, or it can also act as a it can also act as a light concentrator, maybe as a funnel. Okay, you can see the ray diagram. So this kind of diagrams are called a ray diagram. So we will take a light ray which is coming in this direction and hitting and coming back. We will take some sample of light rays and we will find this is the focus. Simple. Okay, and now we can use this to make a telescope, and that kind of telescope, okay, just leave. Here you might have been seen an equation. Any unexplained equations are not for the exam, don't worry about it, because this is just for additional knowledge. That's okay. So just leave it and let's make a telescope. That is main important thing here. So reflecting telescope, you can see that I am taking a pipe or something like this and I am placing a mirror here. Okay, so now let's see here, some object is here, something like a galaxy or something, and the light is coming from here. Okay, so light is coming in this direction and it fell on the mirror. Okay, anyway, it cannot transmit through here. Why? Because it is a mirror. It will be reflected back to this point, and this point is called the focus of the lens. Now if I want to observe this, what is the problem? I cannot place my head here, or I cannot place an eyepiece here to observe. Why? The problem is that if I place an eyepiece here and my head here, I will myself block the light that is coming from the galaxy. So to avoid that, I have to use, not me anyway, it is designed by Sir Isaac Newton, came with an interesting idea, something like this. Let's see. So this was our problem. Okay, so this is our problem. We don't know what to do. And Isaac Newton came with a clever idea that place a tiny mirror, not that big to block the entire light, a tiny mirror which only blocks a fraction of light, so that it can actually reflect the light from here to a side. Okay, now we can actually place another lens which is called an eyepiece. So in any telescope we need actually a second lens. Okay, so that is an eyepiece if you want to do the observation with our own eye. Okay, usually in other telescope like the professional telescope that we use for astronomical purposes, there won't be an eyepiece. So if you go to any observatory like the Keck observatory, or maybe any observatory anywhere, the bigger telescope that used for the scientific purpose usually doesn't have an eyepiece. Okay, you can see the things that is only through a camera, or that is how we need it actually. So that is, then only we can actually record those images and scientifically process it. So that is about the eyepiece. Okay, so through that eyepiece we can observe. Okay, so this clever design is called the Newtonian design. Why? Again, so this is the first kind of a mirror telescope which is made by, the design is actually designed and it's invented by Newton, and this particular design is also called a Newtonian telescope. Okay, Newtonian telescope. And also generally the telescope which uses mirrors are also called a reflecting telescope. I hope you know the answer already, because for a lens telescope, the lens is working on the principle of refraction and we call it as a refracting telescope. And here the mirror is working on the principle of reflection. So that is why we call it as a reflecting telescope. So that's it. Now there are some other different designs of reflecting telescopes are there. So this is the one we have seen already. So the light is coming from here and reflecting back, so that we call it as a reflecting mirror. And this particular design is called Newtonian design. Okay, and this will be, we will be observing it from a side. Here this is a much more different design. You can see the light will come and it will reflect back to the same mirror, and we put a hole in the center of the mirror and we will observe it from the back side itself. And this is called a Cassegrain design. Okay. Okay. So the Cassegrain design and Newtonian design are the most famous two broad categories of telescopes based on its design. And there are many modifications for this Cassegrain design, and the Newtonians are there, but leave it. Anyway, these are the two broad classification. One is Newtonian and the other is Cassegrain. Okay. So this is about the reflecting telescope. And there is one more thing I want to call. Okay, I'm not going to explain the equation for you anyway. So there is something called the resolution of an image. Okay, just leave all this equation. You don't need this equation anyway, but I will explain you what is the resolution of a telescope, or we call it as the resolving power of a telescope. Okay? So that is also an important quantity for a telescope. So that is one of the other reason why scientists are building bigger telescope. Suppose if there are two stars in the sky, okay, in the universe, okay, or simply in the sky in the sense, you know that all the stars that you are seeing in the night sky are not just in the sky, they are actually so far apart, light years away. Anyway, there are two stars, they are close by, so close by like this. So if your telescope has a less resolving power, or if your telescope's resolving power is not good enough, then you won't see it as two separate stars. Instead of it, you will see something like this. Maybe two of them are overlapping. Or you can do this experiment to find the resolving power of your eye as well. Just put two dot in the screen, and if you place your screen so far away after a certain distance, these two dots will appear as a single dot for you. Okay, but if your eye had a more resolving power, then you can see it separately. So the ability to the ability of a telescope to see two close by objects. Okay, here objects in the sense, it can be two galaxies, it can be two stars. Let's take two stars. So the ability of a telescope to see two close objects as two different objects. So that ability is called the resolution or the resolving power of the telescope. So more the resolving power, then we can actually see those individual stars. Okay, otherwise we will see two nearby stars are something like an overlapping star. So this is the same two stars. Actually, here this is with a low resolving power. Okay, resolving power. This is with a high resolving power. Okay. So for a high resolving power, you need a, so here you can see this theta should be small, just leave it. Okay, so if you make d bigger, you can make theta smaller. That means you can even find a very close by objects clear and distinct in your telescope. Okay, so just leave the equation. If you make the telescope bigger, okay, that means the size of the objective lens. I have assume that I have a lens like this, lens 1, and I have a lens like this. This is the lens 2. This lens 1 will have more resolving power. It can be a mirror as well. If it is a mirror and this is another mirror, then the bigger mirror will have higher resolving power, or in other sense, it can actually see those two stars separately, two close by stars separately. That ability of the telescope is called the resolving power. So for resolving power as well, we have to make our telescope bigger. Okay, I hope that is clear by now. Okay, so anyway, that's about the just leave the Rayleigh criteria and all. That is actually not up to your level, because we have to discuss some other things to learn that. Okay, so whatever I haven't discussed purposefully, something like the Raleigh's criteria or some equation regarding the focal length of the lens and all, that won't be there in your exam. So don't get afraid of this equation. Okay, but I have mentioned another equation, that is a simple equation, that is about the what is called the magnification of a telescope. That is, just divide those numbers. Okay, focal length of the objective divided by the focal length of the eyepiece. So that is simple division. I hope you can easily do that equation. There is no need to know about things. Okay. Now I will explain about the mount of a telescope. I will be explaining it simply using a normal telescope. Normal in the sense that an amateur telescope or a casual observer's telescope, something like that we use for stargazing, not for a scientific purpose in general. But I will all that kind of professional telescopes are also working on the same principle. They also have the same altitude and azimuth things will be there. But I will show you here the basic working using a simple telescope, because it is very easy to understand. Okay. So here you can see that you might have been used the camera tripods. Okay, so usually a telescope will have three legs. a stand. Okay, maybe sometimes it can also look like this. Anyway, a stand is needed, and on that stand we will fix the telescope, whether it is a mirror telescope or a or that means a reflecting telescope, or a lens telescope, that is a refracting telescope. We will use something like a stand to hold it, because then only you can point it. But we cannot actually fix it. The telescope has to move in its own axis, then only we can point it. So suppose you are watching moon, and one other kid comes and asks you, or your parent will come and ask you, I want to see Saturn. Then you have to turn your telescope to Saturn. How you can turn it? You can move the telescope completely, or is it better to have something like a moving options there? So that is called a mount. That is the importance of the mount. Okay, so in between that three leg and the telescope, there will be a movable connection between the telescope and the stand, which is called the mount of a telescope. So there are two types of mounts are there. One is called the alt azimuth mount. Okay, so the idea is simple. Okay, you can see that the telescope can actually rotate in this axis. Okay, so it will be something like revolving like this. It is something like the panning movement. And now another movement, we can actually adjust the height of the telescope, something like it can actually rotate about this screw. Okay, one rotation will be about this screw, so it will move up or down. Okay, and another will be something like about this axis, something like here, so that it can move horizontally, something like north to west, something like that. And the other one will be height. So with these two movements, the telescope can point wherever it is designed. Okay, so that kind of a mount is called the alt azimuth mount. Okay, so that is the simple kind of mount. And one more point is that if you start to buying it, if you are planning to buy a telescope, it is better to buy something like this basic mount. Okay. Now let's see another kind of mount is there, that is called the equatorial mount. So equatorial mount is actually a bit more complex in the sense that its axis should be always pointing towards the pole star, or maybe parallel to the rotation axis of Earth, etc. And it will have some counterweight. It is a bit complicated, but once it is set, it is very easy to use the equatorial mount. Here you can see this axis of the mount will be always pointing towards here, and about this axis this telescope can rotate, and about another axis here this telescope will rotate. So its movement is a bit complicated, or you can see here this is towards the Polaris, and you can actually move in this direction and in this direction with the help of that mount. Okay, so that is called an equatorial mount. So why we need this complicated mount when we have that simple mount? Even it is actually not that easy to explain just with this image, as you already may be experiencing. So equatorial mounts are necessary in the sense that especially for long exposure, very long exposures of photo. So if you want to track an object for a long time, it is always better to use an equatorial mount. Okay, so that we can actually make the telescope move along with the object just with the working of a single motor. Okay, so usually for manual telescope, what we do, if you want to go along with that object, if the moon is moving through the sky, you have to move your telescope with your hand along with the moon or the Saturn or the planet or whatever object you are observing. But here there are automatic telescopes where it has its own motor. All the professional telescope already has this. There is no need to move it by hand actually. So it will move with the help of motor. So here for an equatorial mount, you can actually track an object, okay, just with the help of a single motor. So that is the importance of this equatorial telescope. Okay, so these are all an overview of a general idea about a normal kind of telescopes. Normal in the sense I am saying about the visible light telescope, or visible light telescopes are usually called optical telescopes. Okay, they are also called optical telescopes. Now let's discuss about some major observatories that are in the in Earth. I'm not, as you know, the number of observatories in the Earth is, I cannot actually cover that even in a 5-week session or 5-day session. So I will be only discussing the major of them. But and as an additional point, those factual data actually you have to read more about them. Okay, so in that case, I cannot assure you the questions that only from the these slides. Okay, there will be a part of questions will be from the slide. There will be some questions from your textbook, and there will be some from general. Okay, anyway, regarding the exam writing and all these things, I will give you a detailed instruction at the end of our session, and in the sense that, and on Friday, after completing all the syllabus and all, I will give you a brief overview. So don't worry about this exam, what will come in the exam, those things right now. Just concentrate on the subject right now. That's okay. So one of the famous one that is called the Yerkes Observatory. So Yerkes Observatory, the speciality why I included it here, it is actually the largest, just a second. Okay, so sorry, I had some other issue. Okay. So yeah, X Observatory, you can see it is established in 1892. It's at an altitude of 334 meter. Okay, here you will see when you go through the names of telescopes and all, we will see that most of the telescopes are actually situated at a high altitude. So why it is located at a high altitude? Mostly, most of them will be on the top of a mountain and all, because that is where we get less polluted sky. So only there will be less humidity, less atmospheric turbulence. Those things are better when you go to the top of a mountain. So that is why the most of the telescope will be located at a higher altitude. That is one thing. And mostly one more thing, those places will be less populated as well. Why the population is important? Because then only we can, okay, so then only we can actually okay, avoid the light pollution. Okay, now the second thing, when you read about it, you can see that there is a refractor. Okay, that is, here you can see that 40-inch refractor. So X Observatory is an observatory. Observatory means where the telescopes are there. And when you hear about an observatory, that observatory will have may usually have multiple telescopes. Okay, so when you call the name of a observatories like Hawaii telescopes, maybe X Observatory or Devastal Observatory, something like any observatory, there will be multiple telescopes. Okay, so here one of the main telescope is actually 40-inch refractor. So it is actually one of the largest in the size. We call it as a refractor. So its diameter. So what do you mean by 40-inch? So whenever you are hearing the names of telescopes, you will also see that what is the size of that telescope. That is, we won't anyway discuss about the magnification. For any astronomical telescope, actually magnification is not at all an important quantity. The important quantity is actually the what is the diameter of the main lens or the mirror. So that is here 40-inch refractor. So X Observatory has two telescopes. One is 40-inch refractor. Here, see the name. Okay, so I am giving you some points so that you can actually read about them more, even about other observatories also. As well, you can see that it is a refractor. What do you mean by a refractor? Again, you know that it is a refracting telescope. That means it uses a lens. So without specifying that it is using a lens, from this name itself, you can see that it is a lens telescope. Its primary lens or the objective is a lens, and it has a size or a diameter of 40 inch. Okay, the second is actually another reflector, that is 40 inch. You can see reflector means, what is the meaning? That is a mirror telescope. Okay, so that is about the X observatory, and this is another called a large reflecting telescope. Okay, it is actually in again in southeastern Arizona, United States. Okay, it is actually the part of a Mount Graham International Observatory. This is one of the telescope, and this is called the large binocular telescope. Why it is called a binocular telescope? You can see that it consists of two mirrors. It is something like a binocular which has two lenses. Okay. Anyway, you can see that this telescope has the ability, even though it is two different mirror, these two images taken from this two different telescope can be combined to a single image. So it is something like you are looking through a binocular. When you are looking through a binocular, actually you are seeing two different images through your different eyes, but you won't get that feeling of seeing two different things. You will see it as a single image. If you had experience with the binocular, that is the same thing. So what happens there, the brain will combine those two different images coming from your two eyes into a single image. So that is the same thing that is actually happening even when we are observing with our own eye. When we are seeing with our own eye, this is the same thing. Your two eyes will have two different images and it will be combined. Similarly, for large binocular telescope as well, we have two images from two different telescopes, but it can be combined using not the brain but the computer. Okay, here you see the height. It is at a 3,221 meter above the sea level. And one more thing you can see when you read about telescope, especially about new telescope, because we know the exact date on that, that is called the first light. So first light means that is the day on which it got operational, or they built everything, and yeah, now we can do the observation. The first trial of that observation is called first light. It is not the date of inauguration, or maybe the formally it is giving to the scientific community. That date may differ, but the first light means they are actually connecting all these things and setting up everything, and they just give a test. That test, if is successful, then it is called the first light. Okay, here you see the size of the telescope, 8.4 meter. So it is built during 96 and 2002. Here you can see it is in 1982. So in 1982 or even 1968, we had a 40-inch reflector. That means 102 centimeter, or we can simply call it as a 1 meter. So from that 1 meter in 96, we have a telescope of about 8.4 meter. See, that is more than 8 times the size of the that old one. Okay, I'm not saying that these are only the two telescopes, but this is how we achieve bigger and bigger telescopes. So you may think that it is so easy, we just make bigger and bigger mirrors, but that is not that easy. The problem is that even building a big mirror itself is so difficult, because you have to get a mirror, a glass plate, you have to polish it into a curve. Okay, so you have to roughly polish it, then you have to fine polish it. That fine polish should be so accurate, to the level of nanometers. Okay, if you know what is a nanometers, it is actually the billionth of a meter, or billionth of a centimeter. That tiny should be your accuracy of polishing. So to make such a mirror, it will usually take some more than 6 months to 1 year it may take. So it is so difficult to make them, and that is why it is so difficult for making telescope. So it is, even though you are seeing that bigger and bigger telescope, it is not that easy to make. Okay, then this is another one. This is actually you can see that there are different kind of telescope, in the sense that here in this large reflecting telescope, you can see that here this is the mirror. Okay, so this is a single mirror in the sense that they will take a large glass plate and they will carve out that concave shape and polish it, and it has a size of 8.4 meter, and it is called a single mirror. Okay, or we call it as a monolithic mirror. Okay, monolithic. Okay, monolithic mirror. So what is the meaning of monolithic mirror? It will be a single mirror. So now you will get an idea when I discuss about this telescope. Just leave other things here. If you look closely in this, you can see that this telescope is not a single mirror, but it is something like a hexagonal pieces. Okay, if you remember the image of Hubble Space Telescope, sorry, not the Hubble Space Telescope, the James Webb Space Telescope, you will see the similar design there, a honeycomb-like structure. So each of this segment or each of this hexagon is actually a single mirror. Okay, so a large mirror is actually made using tiny it is not that tiny anyway, small segmented mirrors, and this kind of telescopes are called, or this kind of mirrors are called segmented mirror. Okay, segmented mirror telescope. Okay, and you can see that it is also again at a higher altitude. First light you can see, and see the diameter, that is 10.4. so it is actually much more easier to make a single 10.4 meter mirror. It is actually better to make a segmented mirror like this. And this is another, is called the Keck Observatory. So it is sometimes called the twin telescopes of Keck Observatory, not the binocular. There are two similar telescopes are there, okay, of the same this. Okay, and this is also another one. There are two telescopes, and each of them has a diameter of 10 meter. Okay, it is also again you can see the mirror here. This is, okay, it's also a kind of a segmented mirror. Yeah, so that is about the, okay. So there are many other kind of telescopes are there, and now I will introduce you to another kind of a telescope, which is actually called the liquid mirror telescope, which is called the International Liquid Mirror Telescope, which is actually in India. Okay, so this is one of a kind currently operational in the world for astronomy purpose. Okay, so why I am introducing you to this specific kind of thing, you already know that this is one of a kind which is now being operational for astronomical purpose. It is called a liquid mirror. Okay, so unless all the other telescope that you have seen in the previous discussion and all have a solid mirror. Okay, so its mirror is not liquid, but here this mirror that you are seeing here is actually a liquid mirror. Okay, so why it is a liquid mirror? Okay, the concept is so simple. They will take a big bowl. Okay, something like a imagine a bowl, something like this, not a carved one, and they fill it with mercury. So when the mercury is filled, the mercury will reside here, something like this, and the surface will be flat. So as you know, mercury is actually a toxic, as well as it is a reflecting metal, a shiny reflecting metal. So when you start to rotate this bowl, okay, so the mercury will actually go to the surface, something like this. It will make a shape of this curvature, okay, or it will become a curve. I will show you a video. So this telescope will be always rotating like this. Okay. So when it keeps on rotating like this, the mercury will make a curvature like this, and that curved mercury will act as a telescope, okay, or telescope's mirror. So what is the advantage of this telescope? It is so easy to make when compared with that mirror polishing, mirror and all other 6 months long process. It is actually very easy to make this kind of telescope. One disadvantage of this telescope, or the main disadvantage of this telescope, we cannot tilt this telescope. So it will always looking just to the top or to the midpoint of the sky, or the point just above your head. At to that point, the telescope will be always pointing. It cannot be moved to any desired location. Suppose near the horizon, I can see something. If I want to tilt the telescope, that entire mercury will be spilled off. So we cannot actually move, but it is so cheap. Okay, it is usually 1/10th of the price of a usual telescope or a solid mirror telescope of the same size. Okay, so that is the main advantage of having a liquid mirror telescope, and this is an international this is called the International Liquid Mirror Telescope. Okay, so this is that observatory, and this is the telescope building actually what you are seeing. Okay, this is actually located in Devasthal, Uttarakhand, India. Okay, first light is 29 April, and these are all other some. So the size of the primary mirror is 4 meter. Okay, so it keeps on rotating, and rotation period, it will make one complete rotation in 8 seconds. So that is how it is, keeps on rotating. Okay, So that is about the mirror telescope, and this is actually a brief idea about the large mirror telescope, which is actually, you can see in the Wikipedia. Here you can see large binocular telescope that we have discussed here. This is it. Okay, you can see that mirror here. Why? Just a second. Just a second. Okay. Okay, so this is the large binocular telescope that we have discussed, and maybe some other famous telescope. This is the one we have discussed, the Grand Telescopio Canaris, that 10-meter one. This is the Keck telescope. Again, the honeycomb design actually shows that it is segmented. Okay, and the single ones are, as you know, it is a monolithic one. So it is a single mirror. Okay, so here you can see these are a 30-meter telescope, extremely large telescope. These are all actually some planned telescope, planned for 2027 or maybe 30, something like that. And here you can see a very big one. Here you can see an outline, a gray outline, which is called an overwhelmingly large telescope, or OLT, but it is cancelled. And here you can also compare some of the famous other telescopes, something like, see the Hubble Space Telescope, okay, and see the James Webb Space Telescope. See the comparison between this. Okay, so that is about the other telescope, and here you can see the size of a human being in the scale. So then just imagine how big these mirrors are when compared with a person standing nearby. Okay, so that is about the size of a telescope, and astronomers are actually planning. And here you can see the X observatory, that tiny point, that 40-inch one. So see how small it is. And that is how we have different kind of telescopes are there. It is an overview just to see how big all those telescopes are. Okay, so that is about